Welcome back, everybody. This is our second session in NEET previous year questions for chapter Electromagnetic Induction of class 12th. Before this, we have made one video in this series, and that video is available on our YouTube channel's playlist section. We have also started similar series for JEE mains previous years. So if some of your friends are preparing for JEE mains, or if you want some additional practice, then you can go through those questions also. And if you find these videos helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. In the previous one, we completed up to, I think, question number 10. This was the last question. And today we will start with the next one. So here in the above diagram, a strong bar magnet is moving towards the solenoid 2 from solenoid 1. Means magnet is moving towards this solenoid 2. The direction of induced current in solenoid 1 and 2 respectively through the directions. So we have to find out direction of the current in both of these solenoids. Now to find out the direction, what we use? We will use Lenz's law here. So as this magnet's south pole is moving towards the solenoid, and we know according to the Lenz's law that EMF and current is induced in such a way that it opposes its course. So in this solenoid, we will be having south pole induced here. We will be having south pole induced here because towards this solenoid, south pole is coming towards it. So to repel this south pole, there needs to be another south pole. And in this case, now from the solenoid 1, north pole is going away and it will like to stop that. So current will be induced in such a way that it can resist that north pole going away, or in that case, it will be producing south pole here so that it can attract this north pole. Okay, so these will be the poles introduced here. Now to produce south pole and north pole, we know that how direction of the current should be. So suppose we have a south pole, then in to produce a south pole we need current something like this. So current needs to be what we can say clockwise, and to produce a north pole, current should be in the anti-clockwise direction. So now if I try to draw this solenoid in the, we can say in the cross-sectional form, then this is our internal part of the solenoid. This is our internal part or the solid part of the solenoid. And we have a winding here, winding such that Y is here. This is Y. Now, to produce a south pole here, we know that current should flow like this. Means current should travel towards the Y. And if current is traveling towards the Y, means it is traveling from the Z towards the Y. So in the solenoid 2, current will be traveling from Z towards Y. Now coming to the this solenoid, again here we will have south pole. So in this case, let's again try to plot it in the 3D form. Suppose this is the internal structure of the solenoid, and here we have the X, point X. Now the point here we need to consider that in case of solenoid 1, point X is behind the solenoid, and in case of solenoid 2, the point Y is in front of the solenoid. So here this point X is behind the solenoid. So we can say it is something like this. Okay, I drawn it in front. We have to draw it in behind the solenoid. So let me draw it behind the solenoid. So our point is something like this. It is behind the solenoid. Here we have point X, and this is the front of the solenoid. And again, we are producing south pole here. So we know that south pole will be produced something like this. Means current should be traveling towards the X from this, from wires. Current will be traveling towards something like this. So again, here current is traveling towards the X, and it will be traveling from the W. So here current will be traveling from W towards X. Here we have Z to Y. So W, X, and Z, Y. Option D will be the right answer here. Let's move to the next one. An electron moves along a straight line path xy as shown. The ABCD is coil adjacent in the path of the electron. What will be the direction of the current, if any, induced in the coil? So we have to find out direction of the current. And electron is traveling from X to Y. So if electron is traveling from X to Y, as this is a single electron, means we can say if there will be some amount of current that will be flowing in the circuit, and that current will be flowing from the Y to X. That current will be Y to X. And if current is flowing from Y to X, the induced current will be opposite of that. So induced current will be something like this. We can say in anti-clock direction. So it will be A, B, C, D. So A, B, C, D. That will be the right answer here. Now we can take these questions slightly more further, means slightly more advanced, as this is a single electron. This is a single electron. So current will not be traveling for continuously. Initially there will be current, and after that there will be decrease of the flux. Let me explain you how. Let me first clean this. That as electron is traveling from X to Y, suppose electron is this point, electron is at this point. So moving electron will produce a magnetic field, because moving charges produce both electric and magnetic field. It will produce a magnetic field, and that magnetic field is linked with this coil. So there will be induced EMF in this coil and induced current in this coil. Now, when this electron crosses this middle point, after that, before this point, electron was coming near the ring, means flux was increasing. But as electrons moves from this middle point, move away from this middle point, now electron is going away from this ring, means now flux is decreasing. So as electron passes from the middle point, so we can say direction of the induced EMF will change, and direction of the current will also change. So if we have a continuous current in this wire, then option A will be the answer. And if as per mentioned in the question that only one electron is moving, then option C will be the answer, that current will reverse its direction as electron passes through. So in this case, C will be the right answer. Now let's move to the next one. In the figure of circuit, the bulb will become suddenly bright. So we have to find out that when bulb will become suddenly bright. Now to for this bulb to be brightest, what it needs to consume most power. It needs to consume more power. To glow or become bright, it need to consume the highest possible power which it can consume. Now for power we have two methods or two formulas, that is first is V square by R, and second is I square into R. Here R is the resistance of this bulb. Now we will use this one, I square RB. Why? Because as we have inductor in series here, so potential across bulb will not be constant. But we can find out that when current will be the maximum across this circuit, and in that RB is constant. So what we have to do, we have to maximize current in this circuit, and then we can find out that when it will be the highest load. Now, if we examine the circuit, we can see this is a DC circuit. We have a battery here, so it is a DC circuit, and resistance offered by an inductor, that is known as XL. It is omega times L, where L is the value of the inductor. So for a DC, frequency is 0. So here resistance is 0 from the inductor, or we can say value of current in the circuit will be given by this battery. Suppose battery is E divided by resistance of the bulb, because inductor will not offer any resistance in case of DC. But so current will be same, or we can say current will be maximum. But when we press this key, current will not immediately reaches to this value of I, as inductor uh, in inductor current build up slowly, and that building up of the current is given by this equation, that I is equal to I node e raised to power minus t by tau minus 1. That is the charging equation of the inductor. Means after certain time only there will be some current, the current in the circuit will reach to its maximum value. So when contact is made, means when this key is pressed, so time is 0. In that scenario, current is not to the maximum value. Initially current will be 0, because inductor will offer infinite resistance. So B is not right. Option D, won't become bright at all. So it will become bright after certain amount of time when current reaches to the maximum. So B and D gets, we can say, neglected. Now coming to A and C. In A, when contact is made or broken, in C, its contact is broken. So in this, when contact is made, we know that when contact is made, then current will start from 0. So bulb will not have highest intensity or highest current flowing through it. So will not glow to its maximum power. So A again rejected. Now coming to see that contact is broken. So this can be a possible answer, that if contact is broken after a long time, if contact is broken after a long time, then there is chance that current in the circuit will reach to its maximum value, and then bulb will be growing to the maximum intensity. So only possibility is option C here. Now let's move to the next one. A wheel of 20 metallic spokes, each of 1 meter long, is rotated with speed of 120 rotation per minute in plane perpendicular to magnetic field of zero point 0.4 goes. Induced EMF between the axis of the rim and the wheel will be. So we have to find induced EMF, and we have a circular structure here. So it must look like something this. And we have 20 metallic spokes here. So suppose this is our one spoke, and as it is getting rotated, this is one, we have similar 20s here, and if as it is getting rotated, it will act as a there will be induced EMF in it, and so that due to that induced EMF, it will act as a source of potential. So the value of induced EMF when uh, some conductor is rotating with angular frequency omega is given by E induced is B omega L square divided by 2. Now coming, we have the value of B, we have the length, and we have to calculate omega. So it is 120 rotation per minute, or we can say 60 seconds. So in 1 second, there are 2 rotation, or we can say in each rotation there are 2 pi radians. So it will be 4 pi radians per second, or we can say omega is 4 pi. So E induced, and this is the EMF induced due to one metallic spoke. We have 20 such, so it total induced EMF will be 20 times or we can say, let's first calculate for the individual. So E induced due to 1 will be B, that is 4 into 10 raised to power minus 1. Omega is 4 pi into L, that is 1 square divided by 2. So it will be 8 pi into 10 raised to power minus 1. And this is in Gauss. So we will need to convert it into Tesla. And it will be into minus 4. So it will be minus 4 or 8 pi into 10 raised to power minus 5 Tesla. Oh, sorry, no Tesla, volts. This is the value of induced EMF in the one spoke, and we can write it like this, that it will be 2.512 into 10 raised to power minus 4 volts. Now we have similar 20, so they will look like this. Means we have 20 batteries with their negative terminals attached to each other and their positive terminals attached to each other. Now, in case suppose we have some their internal resistance is R, although it is not mentioned here, and as potential of each of these batteries are equal, so final potential will be also equal. Now let's suppose for the calculation that we have 20 batteries, each of which their negative terminals are attached or their positive terminals are also attached, means all of these batteries are in parallel. So in that case, total EMF will be summation ER by RI, whereby summation 1 by RI, where RI is their internal resistance. Now we don't know the value of internal resistance, so we assume it is R. So as we have total 20 batteries, so their sum will be 20 times E of 1 by resistance of 1 divided by summation 1 by Ri. 20 times it will be 20 by R. So R get cancelled, 20 get cancelled, and we are left with E. Means if we attach 20 batteries in parallel of same EMF, of same internal resistance, so there we can say their final EMF or their combined EMF will be same as of a single EMF battery. Only their current will be increased. So as we have only asked the induced EMF, so it will be 2.51 into 10 raised to power minus 4 volts. Now let's move to the next one. A cycle of wheel radius 0.5 meter rotated with constant angular velocity of 10 radian per second in a region of magnetic field zero point 0.1 Tesla, which is perpendicular to the plane of the wheel. EMF generated between the center and the rim is, so we have to find EMF between center and the rim. And again, there is a rotation, so we can write that induced EMF will be half B omega L square. So B is 1.1 Tesla, so 1 into 10 to the power minus 1. Omega is 10. L is 0.5, so 5 by 10 square. So 5 by 10, 5 by 10 divided by these two. So these two get cancelled. 5 by 10 is half, half. So 1 by half, 1 by half into 1 by half. So it will be 1 by 8. And 1 by 8 is 0.125 volts. That is option B for us. Let's move to the next one. So a conducting square frame of length A and a long straight wiring current I is located in the same place and shown in the figure. The frame moves with the right with constant velocity V. Induced EMF in the frame will be proportional. So we have to find out induced EMF. Now let name the sides of the square. So that is A, B, C, D. Now we know that induced EMF is given by B dot L cross V. This is the formula for induced EMF. Now in case of here, velocity of this whole square is in x direction. So velocity is in x direction. Magnetic field due to this wire will be into the page. Using right hand screw rule, we can find out that magnetic field due to this wire on the right hand side will be into the page. So magnetic field it will be in the minus k direction or minus z direction. So let's for AB, AD, sorry, for we can say side AD, here length is in the y direction. So if length is in the y direction, then we can have value of induced EMF. Similar for the CB, we will again have value of induced EMF. But in case of AB, length is in positive or negative x direction. If length is in x direction and also velocity is in x direction, so cross product of both of these will give us 0. Means in the side AB and in the side DC there will be no induced EMF. Only induced EMF only will be there in side AD and side CB. So we need to find that, and we know that induced EMF is BLB. So for AD, induced EMF for AD will be given by magnetic field at this wire AD, and magnetic field at this wire AD will be given by as this is a long straight conductor, so magnetic field is mu node I by 2 pi into the distance. So mu node I 2 pi. Distance of AD from the wire is x minus a by 2. This distance is a by 2. So x minus a by 2 into length into velocity. Now same for we can say BC will be mu node I by 2 pi into x plus a by 2 into length and velocity. So this by solving this we can write like it will be side is a, so length value will be a. It will become mu node I a v divided by pi 2x minus a. This is induced EMF in AD, and this induced EMF in BC will be mu node I AV divided by 2 pi, sorry, pi into 2x plus a. Now coming to their signs, that one of them will be positive and one of them will be negative. And why? Because as this is a closed loop, so there will be a current flowing through this loop. So it can be either in the clockwise direction or either it can be in the anti-clockwise direction. Suppose it is in the, we can say, anti-clockwise direction. So suppose current is something like this. Now this is I am talking about the induced current. So this induced currents decides the direction of the length. So in one of the arm induce we can say direction of the length, this length will be in the positive y direction, and in another arm it will be in the negative y direction. So one of the EMF will be positive and another EMF will be the negative, that we have to consider. So suppose that EMF as this arm is near to this wire, so here magnetic field will be strong, so we suppose that EMF is positive here. In this arm EMF is positive, so that AD is the positive one and BC is the negative one. So our net EMF induced will be EMF induced in this arm minus EMF induced in this arm. So subtracting these two, we will get mu node IAV by pi as common by 2x minus a minus 2x plus a. And it does not matter which you take positive, the answer will be the same, because we have to find only the proportionality. So mu node I a v pi 2x minus a 2x plus a, we have 2x plus a here and minus 2x plus a here. X get cancelled. We have 2a here and it is proportional to 2x minus a into 2x plus a. So that is option D. The induced EMF will be proportional to this value. Now let's move to the next one. A coil in the coil of resistance 10 ohm, induced EMF developed by changing magnetic flux through it. So basically we have been given here a graph of current versus time and we have to find out magnitude of change in flux of the wire. So we have to find out, we can say delta phi or change in flux. So normally when we find change in flux, we do it by method that we calculate the initial flux and then we calculate the final flux and then we can find out uh, change in flux. Or either we can do that flux is equal to B dot A. But here neither we have the value of magnetic field nor we have the value of area, and neither we can say define the value of initial and final flux. So what we will use here, we have to modify the formula slightly and then when we will do calculate this. We know that induced EMF is given by minus d phi by dt, where d phi is the change in flux and that we have to find out. We can write induced current from this equation. Induced current will be E by R, induced EMF by the resistance, and that will be equal to I is equal to minus 1 by R of d phi by dt. And from this we can write that d phi is equal to minus I R dt, or we can say minus R I dt. So we get to the formula that d phi is equal to minus R I dt. We can integrate it to find the value of flux. Now I dt, as we have to integrate I dt here, so integration basically means area under the curve. And we have I versus time graph here. So integral of I dt will be equal to area of this curve, and that area is given by, so total flux will be minus of resistance, that is 10, into area of this graph, that will be half its base, that is 1 by 10, into height, that is 4, so 2 by 10. So from this flux will be minus 2 and taking positive sign, so flux will be option 2 will be the right answer. Option B will be the right answer here. So with this, we end this video here. Hopefully whatever we have covered is helpful to you and understandable also. Again, if you find this video useful, do press the like button, share it as much as possible and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching and we will meet in next video.